Basically talked about sample rate conversion. You can do decimation and downsampling. You can do interpolation and upsampling. I'll say just a little bit more about that in a minute. That's one context in which the decimator and expander are very important. There's another context in which the decimator and an expander become very important, and that's in the topic that we'll be getting to later, which is called polyphase implementation of filters. In talking about polyphase implementation of filters, there's a set of identities related to the decimator and expander that become very important. And those are referred to as the noble identities. And so that's the next thing that I want to introduce. And by the way, you may wonder, should I write this with a little n or a capital N? You know, if you write Fourier, you should write it with a capital F because it's named after Fourier. And actually, I had wondered about this a while back. Should I use lowercase or uppercase? And I called up one of the people who had been involved in the development of these identities. His name is P.P. Vidyanathan from Caltech. And I said, P.P., who is this guy Noble? He said, who? I said, you know, Noble, noble identities. And he said, oh, the reason I called them the noble identities is because I thought they were really noble. And this is called the decimator identity. And I want you to focus on this bottom picture. Don't worry about the equations. The equations are just what we've said before, but you can kind of see the argument, to my way of thinking, is best seen in the time domain. So what is this saying? It's saying if I were to take x of n and decimate it and then filter the result, I would get the same answer as if I took x of n, I filtered it with, not with this impulse response. How is this impulse response related to this impulse response? Well, it's exactly through this expansion. So what I'm doing is taking this impulse response, I'm expanding it out and here, and then I'm only engaging it with every nth point here, and then I'm decimating. So decimating followed by filtering would be the same as filtering with the expanded impulse response followed by the decimation. Now, a word of caution, when you look at this picture, don't confuse that picture with this picture. H of z to the m is not the anti-aliasing filter. Basically, here's the way it works. And this is kind of what you were picturing in your mind or on paper when you were answering that one clicker question. If I take the impulse response and I first expand it out, so here I have it expanded out. I've taken h of n, I am expanding it out here, and then when I do the decimation, that means that I only need to, in the convolution, take the impulse response and march it along by integer multiples of capital M. So that's what the bottom would be. What the top would be is I first take x of n and just extract the circles, and then put those circles through the original filter h of n. So that's the decimation identity. There's a very, very strong temptation that you're likely to have, and I want to short circuit that right now. That temptation is to look at this and say, well, if I have decimation and filtering and cascade, I can interchange the order by raising z to the 1 over m power, because how do I go from this to this? Well, it looks like I take, here it's z to the m, I replace it by z. Well, that's like, if this was z, then I'd replace it by z to the 1 over m, wouldn't I? Well, for all kinds of reasons, the answer to that is no. Somebody in here on some exam might be tempted to do it. Just plant in your mind that, change your wiring in your mind so that if you were tempted to do that, you would not do it. In other words, this expression just simply doesn't make sense. It could kind of make sense if h of z only involved powers of z that were integer multiples of capital M, and then I could think that way, and that's almost what you're doing here, but the general sort of statement is that this expression just simply doesn't make sense. That's the decimation identity. The companion identity is the expansion identity, and this one I'm going to kind of just sort of prove by hand waving. Well, it's actually not hand waving. I'll tell you that the argument I'm going to go through is totally precise, and both of these proofs, the proof of the decimation identity and the proof of the expansion identity, my suggestion to you is get it in your bones, meaning in your visual memory, so that I could almost stop you in the corridor and ask you what the identity is, and you know it involves one of these kind of things, and you could actually almost prove it on the spot, visually. The decimation identity is a little harder, but the expansion identity is pretty straightforward. Decimation identity, the thing you want to picture is what happens with that convolution. Okay, well here, what it says is, if I were to take x of n and filter it, and then expand the result, I'd get the same thing as if I took x of n, expanded that, and then put that through the filter that was the expanded filter, the expansion of this filter. Now, what does expansion do? If I take a sequence, I spread it out, alternate with, well, alternate if it's 2, but in general, interspersing zeros in between, what is that doing in the frequency domain? It's taking the spectrum, compressing it down in frequency, so that what was at 2 pi is now going to be at 2 pi over L. So you get this periodic replication, but it's at a period of 2 pi over L rather than 2 pi. So what this identity is saying is it's saying, well, look at the bottom. Take x of n, take its spectrum, and do that. Take the filter frequency response and do that. Multiply them together. Will I get the same thing as if I first just multiplied this Fourier transform by the filter frequency response and then took that product and I did this? Well, yes. I could do the rescaling either before or after the multiplication. That's where that identity comes from. So you can see it in this picture. If you look at the bottom, well, look at the top picture. We're taking the spectrum of the signal, we're multiplying by the spectrum of the filter, and then we're rescaling the frequency axis to compress it down. That's the top one. The bottom one says take the signal, compress the frequency axis, but then multiply it by the filter whose frequency axis has been compressed. And so that's the expansion identity. I think the important things are to understand what happens in the time domain, the frequency domain with the decimation and expansion, and understand the noble identities, kind of the argument for that justifies them. We're going to be using those identities, and I will tell you that the knee-jerk reaction often is to kind of get the identity in the wrong direction. So kind of get your head straightened out on that so that you can write down those identities, not by memorizing them, but by almost re-deriving them in your head. Or at least I will tell you that's what I do. Because if I just try to memorize them, you almost kind of get it wrong. So you re-derive it. Similar to my suggestion, for example, about Fourier transform properties. Don't memorize Fourier transform properties. Know how to derive them. Now, after you've derived them 150 times, you're going to kind of memorize them. But there was a famous quote by Einstein where he said, why memorize something you can derive? And that's kind of true. Why carry that stuff around in your head? In fact, let me just tell you a story, and I guess this will end up on the tape, but I don't know that I'll leave it there when the tapes are edited. True story. Absolutely true story. When I was an undergraduate, I was in the 6A program, and I went out to General Electric. I had just taken a circuits course, and one day a technician came up to me and he said, can you help me with this problem? Puffed myself up, MIT student, of course I can help you with this problem. I looked at it and I said, oh, you just use Ohm's law. He said, which one? And I felt very intimidated because I only knew one, and I guess in technician school, he learned something much richer. So I said, well, how many are there? He said, well, there are 3. E equals IR, R equals E over I, and I equals E over R. And so what he was taught in technician school was to memorize the 3 Ohm's laws. There was, about 5 years ago, I happened to come across a copy of Physics Today, and this is really true. That particular issue was about the crisis in high school education. And the cover showed a high school teacher. He had written on the board, test tomorrow, the 3 Ohm's laws. And he had the 3 laws written down. So my suggestion with things like Fourier transform properties, Laplace transform properties, noble identities is kind of get it in your head as to where it comes from so that you don't have to memorize it.